just okay. So let me welcome Alessandro, Romito from Lancaster. Okay, so we're already a few minutes after the start. So he's just going to talk to us about entanglement transition from weak continuous measurements. So I'll leave him to it.
Hi everybody.
Oh, before that, let me say that this is being recorded. So if anybody objects, all right.
Okay, so I can start. And I start by thanking you for inviting me to give this talk. What I would like to do in this talk is to present a couple of recent works of mine from last couple of years, from this year and last year, and also some results which is going to be archived soon. And this paper concerned the question which started with other works, and we joined in asking a specific tackling a specific part of this problem, which has to do with the dynamics of entanglement in system in which measurements are present. And the key point, as you will see, is that measurement induced a transition, an entanglement transition. And part of this work is trying to characterize this transition in some specific situations. The work is done essentially in-house here at Lancaster, in collaboration with Martin Sinitsky, a former postdoc here with me, and Henning Schomerus, who now moved to UCL, and Toby Berman, who was master student of mine, and now is studying his PhD in St. Andrew. I think we can start with physics. So I'll start from very far away. You can of course interrupt me and tell me if I'm too far away and to speed up. So the way I see this, the starting of this is in terms of thermalization of quantum systems. So what happens in classical system, we know it very well. If we have any observable and we let it evolve in time, and the phase space is large enough, we have essentially an ergodicity in which the average over time of a certain observable can be replaced with an average of a certain region of the phase space, specifically a microcanonical ensemble of the energies conserved. This is of course referred as ergodicity, and this is the basis on which we do statistical mechanics, and we describe the long-time behavior of certain systems in terms of averages over ensembles rather than averaging over time. Now, if one tries to ask the same question mechanically, the question would be whether the state of a system or part of a system, let's call it A, can be represented in terms of statistical ensemble, and what I wrote in the right. So can you see my cursor on the screen?
Yep.
Okay, so at least I have a way to use a pointer. So the idea would be to see whether part of the system can be described by a statistical ensemble, and mechanically it would be the equivalent of the canonical ensemble would be just described by the Gibbs distribution, E2 minus beta H for some. Now, the simplest way in which people have historically looked at this for quantum systems is rather naive if you think of it today. Quantum system is usually a small one, which is in contact with some environment. So if you wait long enough, the system reaches a steady state in which it thermalizes to a Gibbs ensemble, with the temperature being the temperature of the bath in which it's in contact with. Okay. The approach is of course good, and of course it also describes many experimental situations. Well, what's the problem with that is that it's conceptually this always requires an external object called the thermal bath to make it work. So the true question is whether, if you take a big quantum system but entirely described by quantum mechanics without using any external system, this system thermalizes. So the general feature that one finds in this analysis is the following: you take a big system, you cut out ideally a subsystem A, you call the rest B, the entire system is described by a certain Hamiltonian. And what you do, you take an initial state, any initial state, you let it evolve in time. You do the usual procedure of tracing out whatever is not A, and you do that so that whatever observable you measure locally in subsystem A can be described by this reduced density matrix, in which you trace out all the other degree of freedom. Well, it turns out that quite generically, if you start from any initial state and you wait long enough, the reduced density matrix of the system A, I mean, of course, in a finite size system, what's the problem here? If you have a finite size system, on mechanical, the evolution is unitary, so information is never lost and somehow will come back at some point. So what you do, you look at this. You have to take two limits: the limit in which t goes to infinity, and also the size of the system scales to go to infinity. So you take both of these limits, and what happens is that the reduced density matrix for subsystem A tends to some Gibbs ensemble, in fact. Now, this is true regardless of the initial state. In particular, this is also true if you take an eigenstate of the entire system, A plus B. So this essentially goes under the name, which means that an eigenstate of the entire system locally, the eigenstates will never evolve in time, and locally it will always look like a thermal state. So this goes under the name of eigenstate thermalization hypothesis, which means that eigenstates look thermal states if you look at them locally. Now, the other characteristics of this kind of physics is that if you look at the entanglement entropy of subsystem A, and this is just a measure of that tells you how much a system A is entangled with the rest of the quantum system, you'll find that this will scale with the volume of the region A. Okay, so this is a general paradigm of this eigenstate thermalization hypothesis. But what comes now is that this is not so universal, and there are classes, not just single fine-tuned model, but there's classes of systems that don't follow this pattern. The simplest one is a free fermionic chain. Let me start by this one. A free fermionic chain in which electron can move freely, and you have this hopping TCI dagger Cj+1, just a lattice model describing some kinetic energy of free fermion, but they live in a potential which is disorder. So the potential each side is taken randomly, completely uncorrelated. This problem was solved by Henderson quite a long time ago, and what he showed is that in this system, if you look at the energy eigenstates, they all look localized, exponentially localized around a certain around the position, around the size of the lattice, and they come with a correlation with the length and an energy which depends on the energy alpha and on the disorder strength. Now, because of this localization, there's no transport that can happen in the system, neither current transport of particle densities or spin or energy as well. In particular, this means that there's no thermalization, and whenever you take one of these localized states, it will remain there and will never reach the thermal state because there's no way to transfer energy across the system. What is more recent is that this pattern that was discovered for free fermion is more general and works also in interacting system. So if you think of an interacting system, which is closest we can think to a fermionic chain, is a spin chain, and you can think of a situation like that, and you create an excitation locally. What happens is there are two different competing effects here. There's a unitary part, and you think of a simple Hamiltonian, like an Heisenberg model with some local magnetic field that changes with position in a random way. Now, these two are two competing terms. The unitary parts tend to spread the information or density of energy around, which means a system to thermalize or equivalent to scramble information across a system. On the other hand, the disordered terms tend to do exactly the opposite, so to keep information localized and the excitation localized. The question of what wins between the two is what has been answered in this many-body localization, and it appears that for, close to the non-interacting model, for a certain amount of interaction, the features of localization still persist. Here's another qualitative picture of this. You have a lot of localized states, but each of these states come in the unperturbed model, if you want. They come with certain localization length and also with certain energy. If you want to think of it perturbative, what happens is that the interaction stands can generate null transport by letting you hop, creating matrix element between different energy levels of the unperturbed disordered system. But the point is that matrix elements depends on the distance in energy between this level and also between the overlap of the corresponding wave function, whether the local interaction term is able to couple this term. That's not an easy problem, but the answer is that for perturbatively, for small enough interaction strength, still the localization survives. It also turns out that you can describe this effectively, whatever the system you start with, effectively in terms of localized degrees of freedom that I'm labeling like tau, and you have some interactions between these terms, this term, and what happens is that the entanglement exchange between any pair of these excitation cannot happen via intermediate state, but can only happen via direct coupling between these states. And because they are exponentially localized, this new effective excitation that describes the system, it means that entanglements cannot grow linearly, but at some extensive scaling. Okay, so it will grow with less than the volume of the system, of the subsystem we are considering. And this is generically referred as area law. Okay? So the physical properties that no transport of densities and the conductivity, no transport of densities of energy are possible, it still holds in this case. Good. So there are two different rather generic patterns which have completely different physics. There's that I described so far have been very qualitative, but I just wanted to give a qualitative picture to start with. So we have kind of system described by an energy thermalization hypothesis in which we have an extensive scaling of the entanglement entropy. It's called eigenstate thermalization hypothesis because the eigenstates are thermal locally, and every state essentially appears locally thermal. There's an opposite pattern in which we describe in terms of disorder system, in which states are localized. They don't thermalize, and if you look at the entanglement feature of this system, you see that the entanglement of the states is not scaling extensively with size of certain subsystem, but it rather scales in sub-volume form.
Can I ask something here?
Yes.
I thought
yes.
I thought the area law, you don't need the disorder for that in general, right? You can also have area law.
I use the disorder as an example. I'm just showing you a case where you don't have disorder.
Okay. Thank you.
Can I ask something? So everything, Alessandro, everything you're saying is about typical states or randomly selected states, not ground states, right?
Can you repeat?
So everything that you're saying, I should interpret it as true for a randomly selected state, not just a ground state.
Yes.
Right, thanks.
Generically, yes. So what I wanted to do is to take from this introduction, I want to take the paradigm of the different entanglement dynamics between these two broad class of systems, and look at the entanglement similar transition in a system, but this time not looking at the state or the eigenstates of the system, but looking at the dynamics of the entanglement in the system. And here I introduce these random unitary circuits, which have been studied for quite a while, I would say. The new, relatively new part is the introduction of measurements in this system. So I think the best way I'll go is just to present a model, and let's discuss this model, and let's see what we can learn from it. So the model I'm looking at is a model which has been put forward around 2018 by roughly in the same month. I think it was August of 2018 on the archive. There was these 3 papers, all 3 of them, essentially discussing the same physics. And the physics is the one I'm presenting in this model. So what I've drawn there is an horizontal line which represents the Hilbert space, which represents the physical space of the system. And this, you can think of it like a spin chain. So there's a one-dimensional set of degrees of freedom which have limited Hilbert space locally, generically. Let's be really concrete. This is really a set of spin 1/2 systems. Now, what you have is squares. No, what you have vertical here is time. Okay. So what happens, you have to think of this in terms of quantum circuit, if you want. So you apply some operation to pairs of these objects. So the first operation is a square, and this square is, I think I did it. Yeah. So the first operation you apply is a unitary evolution. And to keep things general, you assume that this unitary evolution is completely random in the space of these 2 qubits. Okay, so it's taken from a distribution which is R measure in U4. Okay, or if you want, this is a circular unitary ensemble of this pair of spin. You repeat this starting. Let's say that you have a finite size system and you label the spin from 1 to n. You start pairing odd, even, odd with the next even one. The second layer now is the measurement part. So what you do here, and these are these diamonds here. What you do, you perform a measurement of the system. Actually, you don't perform a measurement, you perform a lot of measurements, local measurements for each of the spin. So you have all these spins, and now you decide to measure everywhere at every point, and you measure the spin in the z direction. Okay. Now, what happens is that you don't really measure everywhere, but you measure with a certain probability each spin. So you choose a spin, you fix a probability, and with that probability, you decided whether to measure the spin in the z direction there or not. The third and fourth layer, which are essentially the same. The only difference is now the third layer is coupling unitary, even spin with the next odd one. So you do 2, 3 instead of 1, 2 in your coupling. Okay, so that's the difference with layer 3 and 4. Between layer 1 and 3, and layer 4 is exactly the same as layer 2. Okay, so why do we need so many layers? We cannot be enough doing it with 2. So first, let's think of a system without a measurement. What happens here? In this case, you have only unitary, and this is an effective way to model in a computationally doable way the effect of a unitary uniform Hamiltonian, if you want. Okay, so what happens is that in this way, after a few steps, every spin will be essentially coupled to any other spin, and you can essentially mimic the effect of a continuous Hamiltonian, even if a single layer 1 or 3 only couple pairs of spin. Okay. So if you do that and you take just your unitary evolution, what happens? You cannot look at what happens to the entropy of the system. So which means that what I mean is that you take a subsystem of a given size and you calculate the entanglement entropy of this subsystem. Usually what people do, they take the half cut. So you take a system, you cut it into half and calculate the entanglement entropy of 1/2 after tracing out the other half. Now, what I have to say that essentially all what I'm saying here is numerical in this talk. So what you really do, you take a system of size L, you cut it in half, you trace out the corresponding half, and then what you look is the behavior of entanglement entropy after a certain time, because Hilbert space is finite, your entanglement entropy will saturate and will reach a certain value. Now, this value is this page limit, which is essentially means that you have a state taken at random in the entire input space. So you will reach this value of the entanglement entropy, and you will stop there. Of course, you see that this scales with L, which means that in principle, if you have an infinite system, this entanglement entropy will keep on scaling linearly forever. Okay, that's equivalent of a volume law. Any questions so far?
So this is without doing the measurements, or?
That's without doing the measurement. I'm not doing any measurement. That's operator scrambling if you want, or information scrambling. Okay, so the information is essentially dispersed throughout the entire system, the state dispersed in the entire input space. Just a comment, here we have a randomness. So you're making averages over this randomness. Okay, just technical, but it's also conceptual caveat. What you do, you take a system, you take a state, you evolve as a sequence of random unitary evolution. For one of these sequence, you calculate your reduced density matrix and your entanglement entropy, and you repeat this many times. You will generate this set of numbers because everything is stochastic here. There's randomness in U, and you average the entropy. It's important you don't average the density matrix here. Okay, that's general caveat for what I say after. Good. Now, what happens when you put the measurement here? Well, there's a limit. There's one limit that you can very easily understand. Imagine that you measure everywhere. So you measure with probability 1 all the spin at any step. Now, these are projective measurements. So even if in the first step you manage to create a bit of entanglement, let's say between spin 1 and spin 2, due to the unitary, the measurement immediately kills that entanglement and brings you back to a pair of non-entangled state. It can be spin up, spin down, or spin down, spin up. Okay. So again, the next unitary will try to entangle, but the measurement immediately will disentangle it completely. So you already know that if you measure everywhere, no matter how long you wait, you will end up with essentially a state which cannot be entangled with volume law. Okay, so you already know that there is a regime for large P for which a system has an area law. Okay, so the point is that something is happening in between, and what's happening in between is a transition between volume and area law of the entanglement scaling. We're talking about the entanglement after a very long time. Okay, so this is what this paper is reported. And what I want to discuss now is how do you characterize this. First, I want to discuss how do you characterize how do you find and characterize this entanglement transition, and then I will have some question and make it a bit more general. So how do you do that? How do you find this? If anybody has any question?
Yeah, I have a question, if you don't mind. Just to clarify, the rectangular boxes that you have in the scheme that represent the unitary evolution, are these rectangular boxes randomly placed, or they in these checkpoints?
No, the place at which they are applied everywhere, for every pair of qubits. So this box is between, I mean, I say qubit or spin, just they're interchangeable for me. So you apply this box between spin 1 and 2. This is always applied between 3 and 4, 5 and 6. That's the first step. In the other step, you apply between 2 and 3, 4 and 5, 6 and 7, and then you repeat this. You repeat again number 1. So if I have to draw the next step, I will draw a box here, a box here, a box here. I will draw again step 1, then step 2, step 3 and 4. So I repeat this set of 4 everywhere. The position of the unitary is not random. Are the unitary itself that are random unitary matrices? Okay, so they're random U4 matrices.
Thank you. Thank you.
Can I also ask another question?
Yes.
So these 3 different curves that you showed here, these correspond to the 3 different values of P.
Yes.
And does the transition happen at one value of P, or is there a region of P where you have this?
That's all what I'm going to talk about.
Okay.
Now. It's 1 point, but to give a short
Is it
answer,
1/2?
No.
Okay. Thank you.
Can I just ask also about, so you talked about volume versus area law, so presumably that refers to in the finite system, the saturation value of entropy, right?
Yeah. I'll show you that again, yeah. But that's what you do. You in a finite system, you look at the saturation value and you see how it scales with the size of the system.
So the volume law is definitely for the red curve, and what
Yes.
about the blue one?
That's not easy to find, and that's part of the reason why this is not. I mean, it's not easy to find the transition. Can I come? Of course, it scales with the. Okay, and you'll see. It scales with the log also with L. So let me answer quickly. Where is that? Yeah, so this, you see that there's a linear term here for the volume law. If you reach the criticality, it will go logarithmically with L. But this we know only for a certain specific model, as I tell you later, but we tend to believe that that's the case in general. And then when you go below, it generally is really area law. In the system I'm describing, really independent of L, okay? But again, I need some caveat on this, so, and depends on the model, so that's part of the thing I'm gonna say. Okay, now I'm introducing a number of quantities that people use to look at this transition. So the first one we already talked about, there's a way to characterize entanglement between subsystem A and B, and this is the entanglement entropy. There's more general families of, you might be familiar, but there's more general families of entropies that people can use to look at this. It's called Rényi entropies, and are characterized by an index alpha. Now, what is it for alpha going to 1? What you obtain is essentially the entanglement entropy. You have to take a limit to go to 1, so it's a continuous limit of alpha. Being a continuous parameter going to 1, you obtain S. But you can have, for instance, lambda equal 2, which is essentially the purity of your subsystem, and you can construct lambda n. Okay, these are also good quantity and tell you something about the entanglement between A and B. They're good enough. The other quantity that people look at, they don't just cut the system into 2 parts, but look at 2 subsystems A and B within the big system. And in this case, you look at the mutual information, which is still written in terms of entropy. Usually, you construct the mutual information with the entanglement entropy, but you can also construct mutual, let me call it mutual Rényi information, which use the Rényi entropies to construct this this quantity, which essentially tells you about whether there are or there are not correlation information, mutual information between these subsystems. Okay, how do we use them? As I said, most of what I'm showing is numerical, but let me start from this. So this is a mix of results from the paper that I show you, these 3 papers, some from my papers and another paper by Hughes and colleagues in 2019. So let me read through this quantity. How do you find the transition? So what you see in the first plot here, in all plot, I'm plotting quantity as a function of this probability P, okay, which is the probability of doing the measurements. We already know that there are 2 regimes. The probability, the case of P equals 0, in which everything is unitary, and I know it's volume law there. How do I see it here? You see this dashed line, which mark, I mean, different colors correspond to different sizes of the system. And if you look at here, you see that the value of the total entropy, which I'm plotting here, scales with the size n. Okay, you can make a real scaling and show that that goes linearly. I'll show you in the next slide if you want to see it explicitly. You have the other limit in which all the points, which would be p equal 1, in which all the points will essentially collapse on each other and nothing happens. One way to look at, by looking at this entropy, there are essentially a couple of ways that people use to look at transition. One argument is that in both the volume and in the area law, the entropy is a well-defined quantity. It's either this page limit, which is of the order of L, or it's localized a value very close to 0. In between, if there's a transition, you expect large fluctuation. So you want to use the fluctuation of the entropy as, if you want, as an order parameter to distinguish the two. So what you can do, you can look at fluctuation of the entropy for different value of the length of the system and extrapolate the maximum of this quantity for large L. And you see this extrapolation in the inset. So you see the good fit might be 1 over L squared. These are the different points. And you try to fit it and you extrapolate for L going to infinity. The other way is to try to find a scaling of the entanglement entropy as if it was an order parameter, and do some scaling for a given critical value and find some finite size scaling universal exponent, nu and lambda and gamma. Okay, so what you do, you try to fit all these curves in terms of this function with the same value of gamma, nu, and psi critical for all of them. And if you succeed around the critical point, they all should collapse on the same curve. If there's some universality and some finite size scaling of these quantities. Okay, so by looking at this maximum, you can extract a P critical. Extrapolating that, you can extract a P critical also by doing this fit, and this fit will also come with some universal coefficients. That's standard finite size scaling method that you can use in statistical mechanics in general. Now, if you look at mutual information,
sorry, these are projective measurements.
Sorry?
The measurements are projective here.
Yeah, projective, yeah. I'm going away from that. That's the whole point of this talk. If a manager is going away from projective. But let me go step by step. So what you can also do is to look at the mutual information, which is the other quantity I introduced. And these work more or less like the fluctuation of the entanglement entropy. So you expect that this has a certain well-defined value, and you expect a peak of this quantity around the transition. There are two ways to look at this, which is a bit more technical, but what you can do, you can either fix the size of two regions, A and B, and usually because we have, I mean, you see this problem has many of the questions concerning many body localization or the Hilbert space of many particles, you can reach only limited number of sites. We managed to go up to 22. In some cases, we managed to go to 24 sites, which is still better of some analysis of exact diagonalization of system, which is of the order of 12 or 14, but it's still not really a statistically large number of sites. So what you can do, you can either fix two regions, which people even fix to be just one site and vary the distance between them. Or if you have enough data, and you can do it up to 24, you can fix a certain fraction of the entire size of the system, in this case, which is L over 6, and then you scale everything. You scale the entire L. In both cases, you're expected a peak and a maximum. As you can see from comparing these two figures, scaling the entire region works better numerically to determine the value. The dashed line here is the value that you obtain from the maximum of the variance. Okay, so nothing deep here, apart that these are statistical finite size methods to try to find a transition. I have to say that these methods, you can back them up by another system. There is one case in which this is not my work. This is, you can see the reference of people that started looking at that numerically. You can look at this kind of physics in a system in which you can reach very large number of sites, and this is systems in which your unitary operation are not generically any possible unitary between pair of qubits, but you limit your unitary operation to be what's called Clifford algebra. So this is a discrete set of operations that you can perform And in this case, it's because it's a discrete set of operation. I mean, there's numerically you can implement your unitary in terms of just changing some coefficients of your wave function. So this gives you the possibility to numerically simulate a much larger system. And as you can see here, you can go to size of a few hundreds, which are statistically relevant now. The only reason I'm presenting these slides is to show that if you do the scaling, this is the scaling of the entanglement entropy. And this is the mutual information. They scale very well. So statistically, this seems to be a good way to determine the transition, at least in this model in which we can reach very, very large size. So these are reliable entropies, and one can keep them. And that's what we do. We use them also for our smaller systems and trust the results. Okay. Now, here comes a question. I showed you that there is this other system in which you can go very large number of sites and you still see the same physics. There's another system in which you can go a very large number of sites. And this is just if you look at free fermions instead of an interacting spin chain. I write it as like an Hamiltonian because I don't have a better way to describe it. So what you have here, you have an Hamiltonian, which is simple hopping between fermions from site A to site A+1. Now, how do you add the measurement? This is this part in the sum in this box. This is a continuous measurement in which you're measuring the density of particle at each site of your fermions, but you do in a continuous way. So you have a parameter gamma, and you do continuously in time. So at every small time steps dt, you perform a measurement and gives this process is described by a stochastic Schrödinger equation, which is the one I'm writing here, and these W are random binary processes. Okay, so this is a way of describing continuous measurement. I will come to that also in a second if you're not familiar to that. But what is the point is that actually this is the first, this problem has been studied before the other one I presented by Cow and collaborators. And what they find out is that no matter how small is gamma, now you can think of gamma as a way of strength of the measurement if you want. You can compare it with the probability of doing the measurement in the previous models, at least loosely speaking. And what you see that gamma, no matter how small is gamma, your system is always in the area law. So in this system, there's a finite probability, which works as a critical probability, above which you enter an area law, and below which you remain in the volume law, where the volume law of free fermion is completely unstable to measurements in this model. So one of the questions I wanted to try to answer is how do you reconcile this kind of the physics of these two? There are two differences here between these two models. One is there's the peculiarity that these are free fermions, and there are some peculiarity in the unitary evolution. Somehow it is an integrable model if you want. And the other is that you're performing continuous measurements in this model. So what we did is to start from this model and make one step toward this one, which is moving away from the projective measurements and going to continuous measurement, and ask what happens to this transition when we perform continuous measurement. Any questions at this point? Good. Now this is where I don't know whether I go to this is too trivial, but let me spend a couple of lines about what I mean by continuous measurement. So the way you do projective measurement, this is the left part here, and I'm doing it for a single spin 1/2. And you can think of, I just put this figure thinking of Stern-Gerlach, which I think is a classical textbook example of measurements, but you can think whatever way it's more familiar with you. Essentially, you have a spin 1/2, and what you read out, at least in this kind of model, you read out some classical quantity, which is the position on the screen of your electron beam, which depends on the deflection to the magnetic field. Now, the classical interpretation is that particles with spin up are deflected up and particles with spin down are deflected down. So you have a one-to-one correlation between the measurement, between the outcome of your measurement and the back action, which is a projection measurement. So what you describe here, you say the probability of a certain outcome in this case is either x equal lambda, which is this x naught, or minus lambda, and correspondingly, if you get x equal lambda, you project spin up, which is this pi plus operator, otherwise you project spin down. I mean, in a physical way, you can think of going beyond these projective limits and think of what sometimes is called weak measurements. You can think of having a bad measurement, which means that your beam is not very well focused. And in this case, it means that the outcome of your measurement is no more a delta function, but a certain distribution. And in general, the distribution is the superposition of these two. So in this scenario, which is more general, the outcome of your measurement is not either lambda or minus lambda, but it can be any real number along the x-axis. And this is described by a certain probability distribution that depends on the state you're in. So if you are spin up, you will only pick up this Gaussian distribution if you assume the beam is Gaussian. Otherwise, you pick up only the other, but generically you are in a sum of the two. Now, x is cannot only take two values, but it's a real value, a real continuous parameter, can take any value x bar, and depending on the value, you can work out what is your corresponding back action on the state of the system. Now, this can be done more formally. So this is nothing that toy model to describe what's called a generic POVM with a continuous output, which is x, and is controlled also by continuous family, a family of this is a family of POVM controlled by lambda. The point is that when lambda goes to 0, you're essentially not measuring. So you obtain a Gaussian which is pretty much centered around 0. When lambda goes to infinity, namely it's much bigger than the width of your Gaussian, you recover the limit of the delta function. So what you have is a family of POVM that continuously interpolates between a weak measurement, namely very bad measurement, or namely I'm doing almost nothing, and the projective measurement that we showed so far. So what we did is to use this model and replace, instead of measuring with a certain probability, now we do measure everywhere, but we measure with this measurement strength lambda. So we have another parameter that controls the situation. There is one limit in which lambda is infinite, in which you are exactly doing projective measurement, you expect area law. There's another limit in which you're doing very little, but at each site, and you naively would expect volume law. But the question is, what happened with this new parameter? Is there a transition in the system? So we did exactly what I described before with the probabilities, but now using this parameter lambda. So here I plotted the family of entropy that you obtain by generating this system randomly. Okay, so this is how the entropy evolves when you are at lambda. You're plotting red and blue, two different parameters. This is a small value of lambda, and you see that the entropy grows, and actually it reaches a value which corresponds to that page limit. So you know that this is the maximum you can reach in the size of the system you have, and this is what you would, of course, think it's volume law. Now, if you make lambda bigger, you indeed see that you go to an area law. You see that the entropy doesn't grow at all. And if you look at the scaling with the system size, you see that here it's pretty linear, while here, apart the initial value, it seems to be pretty stable with the size of the system. So you would like to say that there's an area in volume law, but you would like to make this statement precise, and that's what we did by analyzing the quantity I showed you before. So the plot you see on the right are the one that I showed you before. The one on the top is just a scaling of, it is a scaling of the finite size scaling of the entanglement entropy. And the plot that you see on the right below is the variance of the entropy. When I mean variance over possible realizations. Maybe this is a point where I should say something important. I said it already before, but here it's technically important and also conceptually important, that when you calculate this average entropy, you should first run one of your random simulation. Then you calculate the entropy for that by tracing out half of the system. You repeat this for all your randomly generated simulations, and you average at the end. So what you have to average is the entropy, not the state of the system. Why I say it's conceptual? If you average the state of the system, you're essentially describing what happened. You're considering your measurement as an external environment, and you are averaging over the external environment, and your reduced density matrix will already look entangled with the external environment, if you want, even if you have true entanglement between A and B. So if you average rho and then you take a trace, you will not be able to find out any entanglement between subsystem A and subsystem B. Okay? I mean, think of the extreme limit. If you have measurements which are very strong and you average over them, your density matrix is essentially the identity matrix. And there's no way that you can extract any entanglement between subsystem A and subsystem B. And this has nothing to do with the volume to area law transition. Anyhow, now we repeat the same analysis for lambda over delta, and you see, I mean, visually you can see the pattern is pretty much the same. And so we can use the same method to extract a critical value for lambda. So we do that, and here reported sum of the value. So you see the value of the critical, they don't need to be the same. These are completely different parameters, but you're able to extract a critical value and eventually critical exponent. I come back to that a bit later. Of course, you always, I mean, there's a caveat with all what we are doing. That's numerical, and that's limited to a number system with size going up to 24, which makes always questionable whether this is the true physics in the thermodynamic limit. But up to 24, this seems to be a clear pattern, and the argument seems convincing. If you do the mutual information, you also get consistent result, which is another way to back up that this transition is there. So you get a consistent value with the variance value. Good. So so what I did now is the analysis in very strong probability 1 and varying this parameter, which is lambda, but I can also vary both simultaneously. I can draw an entire phase diagram in this case of probability measurement and measurement strength, and you clearly see what you expected, and there are two regions which can be separated by a transition line. I need 10 more minutes at most, but is it okay? At least 5.
Yeah, go ahead. I mean, you should be done by 4 for the official bit.
Yeah, no, but I mean, then we need 5 more minutes, and then maybe sometimes for questions. So this is general phase diagram of this system. Why is this in a way relevant going to lambda, including this lambda? So when you do projective measurements, you're essentially, you can see projective measurement are as cutting in your unitary circuit, because you are completely destroying the entanglement. If you perform a measurement here, which is projective, you can see this as a cutting of this line completely, because you're destroying the entanglement between the two. Now, you can therefore map this kind of dynamics to some sort of percolation problem, in which you take your system and you're doing cuts in this graph, and you can ask questions about percolation through this graph. And actually, if you look at the Clifford algebra model, you can indeed see that the model maps exactly into a percolation problem. And in that case, you can use all your results from percolation to look at this transition. Then it becomes an important question to ask whether this entanglement transition is the same as a percolation transition. So you can borrow all universality's features and everything else from there. And our study partially tells you that the answer is no. And the reason is that when you do continuous measurement, there's no breaking of any of these of these lines in a graph, because whatever the strength of the measurement lambda, you're still keeping part of the connection between these parts of your diagram. So there's a formal way to do that, which is look at the Hartley entropy, which is the limit of alpha going to 0 of those Rényi entropies, and this really looks at the support of your eigenvalues of the reduced density matrix. Now that way you can show that in the Clifford algebra model, the two are exactly the same, transition happen exactly the same point. But in our model, you can clearly see, precisely because there's never a cut in the system, that these Hartley entropy is essentially always behaving in a volume law way, which means while we clearly see a transition in all the other entropies, this essentially makes a clear distinction between the entanglement transition and a percolation problem of cutting the bonds of this diagram. So these are two different transitions. And in our model, you already can see that in the R model with projective measurements, but our model makes this extremely clear. Good. Okay, so we did one step. One of my goals was to look at how to reconcile this with the physics of the free fermion model. So we did one step, which is going to continuous measurement, to weak measurements, in which we control the parameter in terms of lambda. But now this model offers us a way to mimic exactly the continuous measurement. Because if we scale our continuous parameter lambda in terms of parameterize it in terms of a rate and the time, then we are effectively describing the evolution of the system in terms of what's called continuous Gaussian measurements, if you want a name for them. But this becomes now a continuous stochastic process, continuous in times, and this is very close to this one. In fact, it is the same thing. If you think of occupation of a fermionic site in terms of spin up and spin down, the measurement model that I described in the limit of dt going to 0 is precisely describing the same dynamics of measurement. Now, the difference between these two models is in the Hamiltonian part, which again is integrable in the fermionic case, while remains non-integrable in a generic case, in a generic spin case. So the last question we asked is whether this might be the difference. So instead of simulating this system that we already know does not have any volume law, but only shows area law, we want to study a more generic situation in which measurements are continuous in time, but the dynamics remains non-integrable. So how you do that? Well, the simple way is just to put an Hamiltonian there. You can put just an Hamiltonian, which is generic interaction between spin, and put enough disorder to make it non-integrable. But we want something more. We want something that can continuously interpolate between the continuum limit and the stroboscopic unitary circuit. And here is where these Poisson kernels comes into play. So we can construct a unitary operation, which is called U, in terms of another unitary operation V. So V is a completely flat, is a unitary operation taken completely from a completely flat distribution of unitary matrices of a certain dimension. So it's taken from the unitary circle ensemble. So it can be the R measure, exactly what we discussed before. With this transformation, you see that you introduce a parameter mu, and these parameters interpolates between the case mu equal 1, in which you reduce exactly to this V, to the case mu going to 0, in which you obtain a set of unitary which are close to the identity matrix, and in fact describe an effective Hamiltonian which has some randomness in it. So if you look at this process in the continuum limit, now you can take mu to scale like square root of dt, and lambda, as you see from the previous slides, also to scale as square root of dt. So this describes continuous measurement and continuous unitary dynamics. And this box tells you exactly what's happening. So you're measuring time essentially in units of mu square, going to 0. So the time is n mu square, where n mu square is kept finite and mu square is set to 0. And now your only parameter is the relative strength between lambda and mu, which is mu lambda naught. So in this limit, you can look again at all your quantities. So first of all, you see that if you take mu small enough, let's say if you take from smaller than 0.1, you can see if you look at the plot of the entropy, they all collapse on the same curve, which tells you that you pretty much numerically reached your continuous limit. And here you see two regimes, the one of very small lambda naught, in which you can interpret this as essentially volume law. You're saturating at a large value of the entropy, while you see here that when you increase lambda naught, the value of the entropy is much smaller and stable here. Of course, we can do a much better analysis, and what we discover, and that's one of the results, we discover that even in this continuous limit, there is a finite value lambda naught critical of transition between a volume and area law. How do we do that? So here is just a plot, and you see visually that here you have a volume law and here you have an area law, and you can also look at the scaling. It's pretty convincing. But here are two quantities that mathematically characterize that. One is usually, as usual, the variance of the entropy. And here I have a more subtle quantity than the mutual information, is a tripartite mutual information. So it turns out that this quantity is always negative. In the volume law, it should scale with the size of the system, while in the area law should scale inversely with the area of the system. Okay, which means that this gives a crossing between the two. That's the best way to find out the point for the criticality. And indeed, we somehow find the crossing. We can give some estimate for this value of the crossing. Okay, so last information is how do, I've showed you several models, and essentially I want to bridge from one to the other in a continuous way. So that's what happens here. Mu is my first parameter that goes from the continuous dynamics to the stroboscopic dynamics. And the example that I showed before is lambda that goes from continuous measurement to projective measurements. So across both these transformations, the transition remains and changes continuously. You can see here, this is changing mu, and you see that, here the volume law, which you can see by changing, it's a bit tricky to see this, but for each color, which is a different value of the measurement strength, you see that here you have volume law going from full dashed dot, here scale as a volume, and here you made an area law, and this behavior is consistent across the entire mu, and so is the dynamics of the parameters we want to look at, which is the variance of the entanglement entropy. So across this mu, we're essentially talking about the same transition. And as I showed you before, when you change lambda, you're also talking about the same transition. So we managed to show that as long as you keep the dynamics of the system like a non-integrable stochastic one, the transition happens at a finite value of your parameters, also in the continuum limit. Okay, so these are the three limits: continuous, this is a stroboscopic limit, but with measurement strength as a parameters, and this is a stroboscopic limit with projective measurements.
Sorry, a question. So in the sort of second column that you have, no, sorry, in that slide, yeah, so one which says stroboscopic with variable measurement strength, but that sort of column also has the P parameter in it, right?
P is 1, that's what I mean there. In principle, you can set a finite P, but the plot I'm showing is P equal 1.
Okay.
So you're measuring everywhere, just telling how much you're measuring. And this is exactly equal to measuring with a certain probability. That's essentially the message of this talk in short. Anyhow, also the scaling for critical exponent works well, apart from spelling here, works well. So you see the critical values are different, but you don't expect to have these to be the same. They can change going from one to the other. What is remarkable is the exponent, the critical exponent, might be here. I'm very vague with it. I mean, again, here there's a limit with can go up to 24 sides. We don't really know what happens in the thermodynamic limit, but the value don't look too different. So given the error of finite size, this might, even at the level of universality, be exactly the same transition. And here I would like to make my my conclusion. So what I essentially showed is that if you look at the dynamics of entanglement in quantum many-body systems in which you have measurements, there is a transition between an entanglement in the steady state being volume law scaling to an area law scaling. This is clear in certain models which are stroboscopic in time. The model in which this is absolutely best known is a model in which you have projective measurements and the evolution happen only via this discrete set of unitaries, which are Clifford algebra. If you try to look at how this in that model, this transition appears to be the same as percolation transition in a graph. If you move away from that limit, which is very specific, it's relevant limit because it has to do with computationally relevant models. If you go away from that limit and look at continuous model in which you try to mimic the dynamics of a continuous system, what we find out is that the transition in which you have projective measurement in stroboscopic dynamics is the same as having continuous measurement in both stroboscopic and continuous limit. The only case, and the transition always happens at finite value, there's a finite critical value of the parameters of the system at which this happens. You can even see that, I mean, at least numerically, you can be convinced that there's a universal parameter that mixes the measurement strength with the probability, and this is essentially square root of p times lambda naught. So the measurement strength works exactly like a probability. You can plot all the plots that I showed as a function of square root of p times lambda naught, and you see that they show exactly the same physics. There's only one kind of system that's let's say singles out in this case, and this is a system of free fermions. But from the results I just showed, this seems to be the case associated to the integrability of the unitary dynamics for this special case. Let me conclude with a remark. I mean, this system, there's one thing that's really missing, and this is some analytically solvable model in which we could make more firm claims. There are some attempts of modeling which one could try to calculate something, but they work in either in all-to-all unitaries, in which you lose the dimensionality of the system, you're essentially going a zero-dimensional system, or there are some attempts in the free fermion models, but as you see, these have all sorts of singularities. So I'm not sure how general the results there can be. And with this big question mark, I would like to conclude. Thank you.
All right, thank you. So
sorry for being late.
Okay, so I think now we can take any questions. I mean, maybe we should, because we're already like 6 minutes over the time. Maybe everybody who is not interested in having, watching a discussion, feel free to leave now, and we can now sort of take questions, or if anybody has any.
I have a question.
Mm-hmm.
So I missed the part because of my connection where you compare against the percolation argument of Nahum et al. So that one is.
I didn't really compare. I just stated it. I didn't really details, but yeah.
So that one is very clear. You have this tensor network that you build and you break it, and it's a percolation transition that gives you as close to an analytical result as you can. So now, of course, if it's not projective, you don't have that breaking of them. That's what I think I heard you say.
Yeah.
So
But I'm saying that the transition is the same.
But the transition is the same. So now I'm a bit intrigued, because what's the underlying physics? That's one question. And the second one that may or may not be related is, if I write a Lindbladian with a generic Hamiltonian and a generic set of jump operators, and I am, and I unravel it in a certain way in terms of pure states, under which situations will I expect to see the transition? Because, before all of this started about 3 years ago, I would have said never. But it seems that you guys have now some more intuition.
Okay.
On the generality. Okay.
Let me see if I manage to answer both. Okay. So the mapping, I think I said something. Okay. So if you have projective measurements, the question is this entanglement transition the same as a percolation transition?
Yeah.
So if this is, I don't know if it's really proved, but you have a strong indicator. How do we look at that? So there's a quantity which is the Hartley entropy, which is this René entropy in the limit alpha going to 0. This essentially counts the support of the non-zero eigenvalues of your reduced density matrix. That quantity is essentially the quantity used to identify that can be mapped exactly to the percolation transition. So it's a quantity you can use to say whether you have percolation transition or not. Okay. So if you look at the Clifford algebra, you can see that all the René entropy, the entanglement entropy, and the Hartley entropy have a transition at exactly the same critical value of probability. Okay? And that's a strong indication that these are the same transition. Namely, the percolation transition is the same as the entanglement transition. Now, let's take another model, which is a model in which the unitary are taken from the R measure, which is what I'm using here. So the unitary can be any unitary matrices here, not only the Clifford, but I'm still doing projective measurements. If you look at the transition for the Hartley entropy, now this happens at a different critical value as compared to all the other entropies, namely all the other René entropies and the entanglement entropy, which already tells you that these two are not the same transition.
Okay.
So the entanglement transition is not the same as the Hartley, as the percolation transition in general. Now, in our model, as you correctly pointed out, this is pretty obvious. Because if you go to the continuous model, I never have a transition for the Hartley entropy. I really have never a percolation transition there. In my continuous model, there's never a percolation transition. If I look at the support, I can show it by showing that the Hartley entropy.
No, it's clear. I think it's clear what you say. Yeah.
It's pretty clear. Yet I still have an entanglement transition, and this seems to evolve continuously from this picture probably. Yeah. You see, if you go to p equal 1, if you go to lambda infinity, so if you look at the very large one, you see this point here, this is the transition that was known before.
Yes.
These are projective measurements. Now this evolves absolutely continuously in this space, so you would call this the same kind of transition in this bigger space. So our transition in terms of lambda is essentially the same transition as the transition due to projective measurements, but this makes absolutely clear that this is not the percolation transition, which I'm not sure is a good news because we know a lot about percolation, but we cannot use much of it in these other models. That's the first question. The second one was about the unraveling, right?
If I write a generic Lindbladian and I unravel it, and what ingredients do I need to have this transition or not? From the
unraveling or from the Lindbladian?
No, in the unraveling, in the pure state unraveling. That's what you're doing with your stochastic trajectories.
That's an interesting question. I'm asked myself. I don't have a full answer, but I think that as long as you're able to write, I might be wrong, but I'm speculating partially, conjecturing, let's say. As long as you're able to unravel your Lindbladian in terms of local measurement of independent measurement of local observables, I think that any of the unraveling should reproduce this physics.
Okay, that's an interesting statement. Okay, thanks.
Yeah, I mean, take it for what it is. It might be incorrect, but my intuition is that any, I mean, the point is that doesn't depend on what kind of measurement you're doing locally. That's my argument. You see that this physics, as long as you're doing local measurements and you have some parameters that can somehow a family of cross operator that goes continuously from the identity to projective measurements, you will see such a transition at some point. Okay. So any unraveling that can be parameterized this way, my intuition is that should give the same physics.
Can I make a couple of comments about the question that one asked and the reply? So the first is even with
I just know who is speaking. I just don't know who.
Oh, sorry. I can switch on the video if you want. Yeah. So the question.
You need to tell him your name as well.
Can you see me? Yeah. Hi.
I can see your name.
Yeah. So even with hard random unitaries and with projective measurements, you can actually show in this all-to-all model that the two transitions are not the same. In fact, they have different critical points and completely different.
Sorry, this is all-to-all.
In all-to-all circuits, but then you can do some field theory and show that in high enough dimensions, the high enough but finite dimensions, the classical calculation transition is different from the entanglement transition. I mean, the scaling is different.
You did it.
Yeah, I mean, Adam, and Jonathan Blumen and Brian Steele.
Yeah.
Did it. And yeah,
you know that better than me. I mean, on all-to-all, I cannot really say anything more than you.
So all I'm saying is that even with hard random unitaries and projective measurements, you can actually show that the two transitions are different. And also,
do you agree that I mean, I think we can agree that in the Clifford algebra, in these models, they look the same. They are the same.
Numerically, they look the same. I agree.
Yeah, numerically, I mean, that's what you can do. Numerically, they are the same.
But it's also, I mean, I'm a bit skeptical about those results because in the case with all-to-all circuits, we realize that you have to go to some insanely large system sizes to see the difference. I mean, we could say it definitively because we could solve it analytically. Anyway, and the second point was you said that if you can unravel the non-unitary dynamics in terms of local measurements, then you should have some kind of measurement transition. But is it under the assumption that the measurements always try to decrease the entanglement? Because there are these other models, there are these other measurement-only models where you have local measurements, but not necessarily single site. And those measurements are such that they try to entangle the 4 or 5 sites they try to act on, and that necessarily, and there is a transition there as well. So I can sort of take.
Yeah, but these are still local. I mean, let's see if I understand correctly. I mean, my answer was in terms. I mean, okay. So I can still confirm my conjecture in the case in which I measure single qubits, and I think on this we kind of can agree. So if I make unitaries and then I make unraveling of measurement on single qubits, then I think it's pretty. I still think that what I said is correct. If you make measurements of pairs of qubits, now, I mean, at least numerically in the, I didn't do that, but in some of the works that I mentioned, still not all-to-all, just one D system and then measuring locally, where locally, I mean, pairs of qubits like this, you can build measurements that on pair of qubits project the system into the Bell state. So you still retain some entanglement. Still entanglement on pairs of qubits, and also in this system you see a transition from volume to area law.
Exactly. So
as long as you make measurements which are local, it doesn't matter whether you measure on. As long as your measurements are a local set of qubits, doesn't matter whether you measure on an unentangled state or entangled state on this local subset of qubits.
But doesn't this also mean that if I have a generic sort of okay, I shouldn't say generic, but if I exclude single site measurements from my game, then it can very well be that there is no aerial or phase, because the multiple sites.
Also, sorry, I mean, also when you have measurements of pair of qubit, there is a transition between volume and area. They find it, unless I remember it wrongly, but.
So I was thinking about this paper by Sarang Gopalakrishnan and Vedika Khemani, David Hughes, and someone else, where they have transitions in a measurement-only model.
It's measurement only, okay.
So there, basically, the point was that even if you have local measurements, not single
measurement only. Measurement only, I think that you can. So your statement is measurement only. You don't have the volume.
No, they have a transition.
Yeah.
But I was thinking that if your measurements are sort of, if you exclude single site or two site projective measurements, but include 3 onwards, then you may not have an aerial or phase.
Yeah, can be.
But 3 sites or 4 sites is still local, and I find this a bit confusing because this is not. I would not say that this is qualitatively different from a single site measurement, but that's what they find, and I don't understand. So I was just asking if you have insights on that.
Well, I mean, honestly, I have to say that I don't know the work very well, so I cannot add much to what you said.
Okay, yeah, it's just making the point.
So that's my honest answer on this. I'm not sure why I'm on these slides.
All right.
I had another question, but okay, let's go ahead.
I want to ask if anybody else wants to.
No, so I had another question, and you said it in the talk, but it will be nice if you can summarize that once again. So you had this parameter lambda over delta, which you used to interpolate between the weak measurement and the strong projective measurement case.
Yeah.
But then there was another sort of interpolation in a different direction, which was between discrete dynamics and continuous dynamics. Can you sort of summarize what was the parameter there and how did you scale?
Yeah, so there are two steps here. Yeah, you got it absolutely right. So probably this is the one. That's probably the one where I want to go. So I mean, probably should have put the two figures together, but I think this is one of the figures. So this is a figure in which, I mean, originally you would see only. Maybe I can ask. Let's see if we manage to do. So originally, you would have, if you look at before our work, you would have looked only at this part, that line up there. That's how your transition would have looked like. Okay. Maybe with some, maybe you should have P as well. Exactly, something like that. So for small p, you're still volume law. Then there is a transition here, and then you enter area law. What we try to do is to use this parameter lambda, and this continuously map this transition to another transition, which happened with probability 1 now. Yeah, with probability 1, but with another parameter, which is this measurement strength. Let me call it like that. Now, you're right, there is another parameter. So what is this model that we come up at this point? This is a model in which we are still stroboscopic. So we take a chunk of time, delta t, we do a big unitary transformation, which can be any unitary of 2 qubits. So it can be very far from the identity. And then we do measurements. And this measurement can range from being something very close to the identity from something very far from the identity, which is projective. So the measurement has built in this parameter that let it be very close to the identity, but the evolution is always essentially a big entanglement step. I mean, I'm talking in very qualitative terms. Now we introduce this other parameter mu. I mean, this other parameter mu, the point of this other parameter mu is to make the random unitary continuous as well. Now, as I comment here, well, this changes the parameter. As I commented here, in principle, this part of the what we did with the measurement, if we scale the measurement strength with properly with time, we are obtaining what is called a continuous measurement. These are measures. This is an unraveling of a Lindbladian, if you want. That's precisely what it is. So you can get from that model to a model which is an unraveling, a stochastic process that unravels the Lindbladian. What you're missing is this part here. That if you take random hard measured unitaries, they don't correspond to any evolution of an Hamiltonian in a simple way. Now, what you can do, you can take just an Hamiltonian, just put the Heisenberg model in random local magnetic field in any direction.
Yes.
But the point is that there's no way, if you do that, you have no parameter that will take you to the hard measure.
Sure.
If you take this model, it's not obvious that you will obtain the hard measure, even if you put a lot of, especially if you put a lot of local fluctuation. If you look at the probability distribution of this 2 qubits model, you will not obtain the hard measure. So we're looking at something which was a bit more, something that could continuously interpolate. And actually it exists, and it does based on the fact that you try to maintain probabilistically maximum entropy at each stage, at each value of mu. So you have this transformation, and this transformation does two things. In one limit reproduces your unitary stroboscopic. In the other limit, it reproduces some correction to the identity metrics, which are still stochastic. So it's like an effective Hamiltonian, because the correction are Vannier process linear in dt with a certain effective Hamiltonian. Now, what's the point? That this Hamiltonian is stochastic and absorbs the stochasticity from the original unitary V. Okay, so it turns out that if you look at this stochastic process, it's a Cauchy process. Okay, it's a Cauchy stochastic process. If you would do this one, would be another binary process. Okay, so it's a different process, and actually we did some work there. We show that even if you take a continuum limit of a unitary evolution from a binary process, you obtain exactly, and you try to match. Now you have a parameter here, right? This is a stochastic process, so there's a parameter that tells you what's the fluctuations of this process. If you match the fluctuation of the Cauchy and the fluctuation of the binary such that you have the same Lindblad, if you want, then you have the same behavior, namely the same critical value of the transition. Okay, so in this way, it's even more universal. It doesn't depend on which stochastic process you put. At least comparing two different stochastic processes in the continuum limit, they give you exactly the same lambda naught. So now everything boils down to one critical parameter, which is this lambda naught in the continuum model, which is just a ratio of your, if you want, is the rate, the measurement, the inverse measurement time, if you like. And I think the most convincing one is probably this one. Yeah. So you can change also mu continuously. And you see here, the way to see this, maybe I should do it. I'm doing something by hand very much.
Yeah, okay, I see this. So but this sort of construction, or the way you, no, I shouldn't say construction, but the way you approached this was basically you went to p equal to 1 and appropriately defined the time continuum limit with the strength of the measurement, and you defined this Poisson kernel to take the continuum version of the unitary dynamics.
In some sensible way, yeah.
Yes, but is there a way in which, if I was not at p equal to 1, I could also sort of push it into the lambda naught or effective lambda?
Yeah, it works for any p. I mean, I don't have to. I need to go now. Don't let me go to my own. But if you go, I should dig this figure from. I didn't have it here, but you can get exactly.
Okay, I mean, you can just tell me that if it's yes or no, and I can look at the paper.
No, I can. No, but I can make a statement. I don't have the figure to back up what I say, so you have to believe me. But you can replace the parameter lambda naught with lambda naught times square root of p, and you reproduce for any finite p exactly the same plots. So p is part of the game also in the continuum limit.
Okay, yeah, that's what I was looking for. Yeah, thank you.
So I mean, it's really, you really go from the continuum to the stroboscopic projective without ever jumping in this kind of transition. So everything happens smoothly.
That answers my question.
Okay, so yeah, I was going to ask if anybody else. If not, then well, thank you for the talk. It was very interesting. One to go, but he also said to thank you.
Thank you very much for listening for such a long time.
This was a very
much appreciated.
It's a very interesting talk. Yeah, thank you. So is the second